My name is Raghav, and today I'll be presenting our work on leveraging polarization of Wi-Fi signals to track multiple people. Recently, a number of human location tracking techniques using Wi-Fi signals have been proposed. This is because Wi-Fi is already quite ubiquitous, so there is no extra hardware needed for tracking. However, these techniques can only track locations of a single person. And among those couples that can actually track a few persons, they still need to know the number of persons or track only moving people or can interrupt regular Wi-Fi communication. So due to these limitations, our motive is to design a passive commodity Wi-Fi based multiple person location tracking system that does not have any of the aforementioned limitations. Here is an overview of our proposed technique. Assume that we have a deployment of one Wi-Fi transmitter and two Wi-Fi receivers at known locations in an environment that is occupied by multiple people. First, a Wi-Fi signal transmitted by this transmitter will reach a human body and eventually reflect off towards the two receivers. And because of this, the two reflected paths eventually make two angles with the line joining the two receivers. And thus, since we already know one of these sides, we have a triangle with two unknown angles. These unknown angles are called the angle of arrivals. And if we can measure these angle of arrivals, we can essentially track the location of a human. So our technique largely involves three steps. First, we estimate the angle of arrivals of all human reflections at both the receivers separately. Then we pair up the angle of arrivals for each human. And finally, we solve the triangle to locate the human and then estimate the trajectory. Now, since the angle of arrival can be measured for both moving and non-moving targets, our approach can track both moving and stationary humans, unlike prior works. However, implementing this approach has multiple challenges. The first challenge is that as a person moves, the angle of arrival can move quite quickly, and this can cause blurring, and this reduces the location accuracy. Second, two closely spaced humans can have very similar multipaths, and so it becomes very difficult for us to clearly separate them out. The third challenge is that when there are multiple targets, there can be multiple angle candidates at both the receivers, and it is hard to pair the angle of arrivals for the same target. And finally, because of the presence of noise on commodity Wi-Fi devices, sometimes even if we have two separate trajectories for two different targets, the potential of certain noise points can eventually cause the paths to merge. So in order to overcome these challenges, we propose two ideas. The first idea solves the three challenges, and the second idea proves the last one. Let us now briefly examine the two ideas. Our first idea is to introduce polarization diversity in the Wi-Fi channel. Existing approaches use a vertically polarized antenna, but we propose to use dual polarized signals. The reason is that when a dual polarized signal arrives at a target, the human body has different vertical and horizontal cross sections, and so it reflects or changes the plane of vibrations of the signal, and thus the polarization angle or the PA is changed. Consequently, different targets generally have different cross sections, and so even if two targets are quite closely placed, they will have slightly different PAs, and therefore that will help us to disambiguate or separate out their multipaths more carefully, and this solves the second challenge. Finally, once a signal arrives at a reflector and the polarization angle changes, this angle is always a ratio, and this ratio does not change over space. And so if you were to take multiple snapshots with similar polarization angles and then extract the corresponding AOAs, we can solve the AOA blurring problem. And finally, in order to get the AOA of the same target, we just observe the polarized signal from two different receivers. And if the polarization angles are very similar, then we take the corresponding AOAs to do the matching. So these solve the two problems. Finally, in order to solve the trajectory estimation problem, we formulate that the true location is hidden from us, but the implied location from an AOA pair is observable. And so we aim to find the probability of true location given the implied location in the presence of noise. Now, due to time constraints, I'll present a highly simplified flow. Please refer to our paper for more details. So we basically assume a hidden state model where the location, which is hidden from us, is actually influenced by both the movement of the person as well as the clutter. By incorporating the clutter, we reduce the chances of having those erroneous merges. Then we use a state-of-the-art filter called a GM-PhD filter, which uses a series of Kalman filters to figure out the probability distribution of a particular point associated with a particular state. Finally, after multiple measurements, the trajectories are refined and the filter can output the locations of the different human targets. We now move towards our implementation details. We used polarized antennas, and we had over 5 participants in 3 environments, and we used the HTC Vive for ground truth. And for the performance yardstick, we use a tracking error, which is the Euclidean distance between the ground truth and the location estimate. And in this figure, we show the CDF of the tracking error for both the cases of with polarization and without polarization. We find that the median tracking error was 56 centimeters with polarization versus 97 without, indicating a 40%, 42% reduction in the tracking error with polarization. Finally, we see the tracking error for tracking 5 persons with our scheme, and we find that for up to 4 persons, the median tracking error was always below the median tracking error of single person tracking scheme of WiDAR2, which is around 75 centimeters, and only for the 5-person tracking case, the error jumped slightly to 78 centimeters. So to conclude, we propose a solution to multiple person tracking using Wi-Fi, using signal polarization, and had a median tracking error of only 56 centimeters.